Okay, well, it's all right. So we can talk about this stuff that we just discussed. Hopefully things will be back. Maybe I should call. Right, let me see. Hi, we don't have projection anymore in 104. Yeah, they turned off both of them on their own. Sure. Okay, so any other questions from the moment?
I don't understand the calculations at the moment.
Yeah.
Just based on that bracket question. And maybe it's just a core concept, but in this situation, you're describing pulling the bracket all the way around now.
Yeah.
So why would I want to rotate it?
Well, that's because it'll be easier to take it out that way. You will still apply a force, right? But you know it's sometimes easier to apply a rotational force, which is the moment, to take it out. Because if you are, let's say, applying, let me put it this way. If you have something that is inside, and that was a bracket, right, we had. So something that is inside like this is called a cantilever. We'll talk about this, right? And cantilevers, they basically can exert a torque in the opposite direction. So you want to counter that torque. This is a cantilever action. If it was like a hinge, you won't need to apply a moment because you could just push it and it'll rotate freely. But this is cantilever. So cantilevers, basically, they apply a torque in the opposite direction. So to really take it out, you have to apply a moment. You see what I'm saying?
I guess I'm confused of how it's fixed to the bottom point.
Yeah, that's the confusing part. Is like, where is it coming
How
out
is it
from?
fixed? Am I looking at something that needs a linear movement moved up out of the ground type thing? Like pulling
Not necessarily. Not necessarily. So okay. So let me. You're actually chasing the wrong question. Let's not worry about how it is fixed, right? The question is, if I'm applying a force, how can I maximize the moment about that point? That part you understand. So, okay, so when we talk about the support reaction, so there are two kinds. All right, thank you. Yeah. So, do you know what the problem was? Okay. All right, so there are different ways you can attach something, right? This is one way you can attach. So if you attach it this way, this is basically a hinge joint. In that case, you don't need any moment. But if you fix it inside, it's a cantilever. And that cantilever can resist the rotational motion, right? So that means that if you want to really take it out, you will be better off applying a moment to oppose that torque.
Isn't it constrained coming out the hole though?
Well, I mean, if you say that there is like a gap over here around this thing, then you can just push it out, right? That will be fine. Then you don't need a moment. Yeah. But anyway, it's not important how it is attached to the ground, right? That's not important. Okay, other questions? The moment captures basically the force that you're applying and the distance from the pivot point to the line of action. So it captures both of them, right? As we said, if you just apply the force at the pivot point, there is no way you can rotate that object, right? So you need to be farther away from the point of rotation so that you have a moment. So the moment is that physical quantity that tries to capture the notion of a force applied as well as the perpendicular distance. So the longer the perpendicular distance is, longer the lever arm is. So you guys were probably on seesaw when you were a kid, right? So when you were on a seesaw, even if you didn't weigh as much, but if you were farther away from the point of pivot, you could come down, right? And that's the same thing. So when you go farther away from the point of pivot, you're applying more moment, and that means you'll be rotating more.
But the moment is perpendicular to the plane of the force.
Right.
So the force has to cause rotation, basically.
Right. So force does cause the rotation, right? So if this is, let's say, your seesaw, and you are hinged over here, right? This is the point, and you are sitting over here, and you have a friend sitting over here. You know, your friend could weigh much more than you, but because you're farther away from the point of rotation, you can still bring the seesaw down, right? Because if you compute the moment due to your weight about the pivot point, it is going to be your weight times that distance L2, right? On the other hand, the moment of your friend would be his or her weight. Let's say this is m1 times g, this is m2 times g. We'll do this stuff pretty soon. Then the moment due to your weight is m2g times L2, and the moment due to your force is m1g, the weight times L1. So even though m2 is less than m1, because L2 is much more than L1, you can still bring your side down, right? Because the net moment is going to be in the clockwise direction. If you add the two moments, the net moment will be in the clockwise direction. And if the two moments are perfectly balanced, then you guys will be absolutely horizontal, right? Now you'll have the bracket dreams tonight. Yeah. Okay. All right. So again, we'll do a few more examples where you'll see how we can use all these moment calculations, the lights. Oops. That's not what I wanted. Good.